Today, we're going to do practice problems involving the Diels Alder reaction. These can be some of the harder problems in Orgo 2, but they also can be done pretty systematically. So I'll give you a lot of problems to practice, as well as some tips to help along the way. To start, try to find the product of this reaction. I encourage you, with all of these problems, to try to find the solution on your own before I show you how I would go about doing these, especially as they start to get harder. I said earlier that these problems can be done pretty systematically, and that's because all of the products share a common feature, and that is this cyclohexene with variable substituents. The hard part is identifying which carbons in the reactants correspond to the given carbons in this cyclohexene. From there, you can just plug in the substituents. And that can be done pretty easily using this key, in which a diene containing this structure reacts with a dienophile containing this structure to form this cyclohexene. But before we can just plug and chug, we need to identify where the diene and dienophile in our reactants are. So the Diels Alder reaction requires a cis diene, or like a cis conjugated carbon system. But a lot of times on exams, your professors might show you a trans conjugated carbon system. That's okay, because to turn this trans system into the cis system, you just need to add heat. You heat it up, the bonds will break, and it will reform into the cis form. And that works out perfectly because, actually, I forgot to write this down earlier, but the only thing you need to run the Diels Alder reaction is heat. So heating up this trans diene will lead you with the same product as you would with the cis diene that is necessary for the Diels Alder reaction. So this is our dienophile, and you'll come to know that it is very beneficial in these problems to number your carbons, especially when using this key. So 1, 2, 3, 4. If we look at our key and the dienophile there, we can line up these carbons we just numbered with the ones on the dienophile of our key. This might seem like an over complication of what we're doing right now, but when this dienophile has substituents coming off of it in different directions, numbering these carbons is really, really, really helpful. Now for our dienophile, we're just looking for this double bond system, and that's pretty straightforward. We found that here. I want to say, though, this is not the most reactive dienophile. We'll talk about why pretty soon, but in this reaction, this is the dienophile. And just like before, we're going to be numbering the carbons, but we're only numbering the carbons that appear in the key, so not the substituents. And that would go like this: 5 and 6, 5 and 6. And you might be wondering why I went straight to 5 and 6 instead of numbering them 1, 2, 3, 4 like we did with the last starting material. And that's because these carbons can be written over in our product as such. So when we're drawing out our product, we can start with the key. We can number the carbons and know exactly where the core structural carbons from the reactants went. Now we just need to plug in the substituents. So in the diene, so carbons 1 through 4, there are no substituents. It's just the diene with nothing coming off of it. However, for carbons 5 and 6, each carbon has 2 methyl groups protruding from it. Therefore, in the product, we can leave carbons 1 through 4 alone, but draw 2 methyl groups coming off of each 5 and 6. And so we can conclude that this is our solution. Quick note, this looks pretty weird. That's because the methyl groups are actually not in plane. I just didn't indicate the stereochemistry because they aren't adjacent to any stereocenters or chiral carbons. There are, however, problems in which the stereochemistry is very important. And we will do a lot of those later on in this video. In fact, we're moving on to one of those right now. Here we go. Let's try this next problem. Same deal. Give it a shot on your own first, and then I'll show you how I would do it. Okay, so with pretty much all of these problems, we can use the exact same template. We can use the same template. So we're looking for a conjugated carbon system or a diene and electron donating pi bond or dienophile in our starting materials. And if you do that, you might notice something's off. You might run into an issue because there are 2 conjugated carbon systems in our starting material. There's this one, 2, and there's this one, 2. The question becomes, which one is our diene? Now, you probably recall in the last problem, I mentioned that the dienophile we had there, which is this, was not the most reactive dienophile. And that can be explained through the mechanism of the Diels Alder reaction. To be brief, you have essentially a rotation of these marked electrons in which the dienophile not only gives, but also takes electrons from the diene. So you have sort of a resonance hybrid intermediate that looks a lot like benzene because the electrons are moving, and you end up with this product that matches that of the template, and the new electrons or the new bonds are color-coded to match where their electrons originated. The key, though, is in this resonance interaction, like between these two, because it implies that the dienophile needs to be able to accept those electrons for the reaction to occur. Now, you might be able to better understand why this dienophile is not the most reactive, because it is adjacent to 4 methyl groups, which you may or may not remember from the idea of conjugation, but methyl groups are electron donors, so it slows down that reaction. Now, we might be able to think in the opposite direction and say, okay, if electron donors slow down the reaction if they are on the dienophile, then electron withdrawing groups on the dienophile should stand to speed up the reaction. And you would be right. And we can apply that to this problem. The diene on the left is adjacent to 2 electron donating methyl groups, while the diene on the right is adjacent to 2 electron withdrawing carbonyl groups. Therefore, this structure is more reactive as a dienophile and in turn will act as the dienophile. Now we can go back to our numbering convention as such. So the left structure is the diene, so we can count 1, 2, 3, 4. Now moving over to the dienophile, we only need to focus on one of the double bonds, which is easier in this case because it is symmetrical, so each double bond looks the same. So we can do carbons 5 and 6. Note ahead of time, we could flip it so that we have carbon 5 and 6 like that. just know that that would lead to two different answers. And so we have two different answers for this problem. And so just like the last problem, we're gonna fill in the template, starting by numbering and then filling in the substituents. So carbon 1 has a methyl group and a hydrogen. Carbon 2 has nothing. Carbon 3 has nothing. And carbon 4 has a methyl group and a hydrogen. I'm writing in the hydrogens this time because I think that it's helpful, or it will be helpful when we cover the stereochemistry. Now moving on, carbon 5 has this whole structure on it. So we can draw that in now. Also, as well as a hydrogen. And carbon 6 only has the carbonyl with hydrogen also. Okay, so with that all drawn in, this is the structure, the constitutional structure of the product. However, notice I did not draw in the stereochemistry. That's something we need to worry about now. Now, this is how I'm going to explain this. It seems like there's a lot here, but there are really only a few major rules that you need to worry about. For the diene stereochemistry, I want to offer a mnemonic. To get there, though, I first want to point out that at the end of any sp2 hybridized carbon, or at the end of a double bond, you have two substituents. Oftentimes it's a hydrogen or two hydrogens, or there's something else. We just don't always indicate the hydrogens. But the point is that there always are two things there. So the mnemonic here is that the substituents that are on the inside are close to each other, so that's C. So they're going to come towards us. And to draw that, we simply need to put them on a wedge. Likewise, the products that are facing away from each other are going to go away from us in the product, and we draw that with dashes. You can also do that even more, like in a different mnemonic. You can replace the A's with F's and say the products that are far away from each other will face away from us. Now for the dienophile, this can be tricky, but it really becomes more simple if you focus on the template. So when the dienophile has a group or an electron removing group that is sterically larger than the other, you can reasonably conclude that it can form one of two possible products. The first, where the substituent is moving into the page, is the endo product, into endo. The second, where it moves out of the page, is the exo product, out of exo, like it's exiting the page. Most of the time, the major product will be endo. So let's apply those rules to this problem. So the methyl group on carbon 1 is on the inside. So it's close, so it's going to come towards us. Alternatively, the methyl group on carbon 4 is on the outside, so it is away. Therefore, it should be on a wedge, or a dash. It should be on a dash, sorry. Now, carbon 5 has the sterically larger electron removing group. Therefore, it is more likely to be endo, which would force carbon 6 to be exo. So this is a solution, a major product. Note the alternative where carbon 5 is exo and carbon 6 is endo is also possible. For this next question, I'm giving you a cyclic product and asking you to draw the starting materials that would yield it. Once again, give it a shot on your own and then come back to me. Good news, we can still use our template. The only difference is that this time we just do it in reverse. We still number the carbons that we know within the ring, as well as their corresponding carbons on the other side of the template. Now we just have to add substituents to the carbons on which we know they exist. So looking at our template, the only carbon that has a substituent is carbon 2, which has a methyl group. So in our starting material, carbon 2 will have a methyl group. Therefore, our answer can be written like this. Let's do another one in that same format, just this time it'll be slightly more involved. Just like the last problem, I'm going to start by drawing the template out. I then can number the carbons on the product that we know, but hold up. How am I going to number this? Because this doesn't look like this. The template calls for a cyclohexene, which has one double bond, but this product has two. And the issue here is that we don't know which double bond, like whether it's A or B, is representative of this double bond in the template. So our first task is just going to be figuring that out. So let's just focus in on the product to figure out how we can determine that. If we were to ignore everything outside of the cyclohexene system, we would have this, a cyclohexadiene, which is identical on either side. You could flip it either way and it would look exactly the same. So this tells us nothing. And that tells us that we need to be focusing on the substituents to differentiate them. So what's different between these two substituent groups? Double bond B is adjacent to an alkane substituent, while double bond A is adjacent to two carbonyl substituents. And I would ask you, where have we seen carbonyls before in this video? That's right, they are great electron removing groups because the oxygen is highly electronegative. And what's the deal with electron removing groups? They speed up the reactivity of the dienophile because they activate its ability to accept electrons from the diene. Therefore, it is much more likely that the region of the product adjacent to the carbonyl groups is the dienophile. And in turn, the rest of the molecule comes from the rest of the ring rather, comes from the diene. So we've confirmed that double bond A is associated with the dienophile and double bond B is associated with the diene. But if you look at our template, we always have the diene on the left and the dienophile on the right. You don't have to do this, but it makes it a lot easier to do this systematically if you keep it aligned like this. Whereas in our given product, A, which is associated with the dienophile, is on the left, and B, which is associated with the diene, is on the right. So to make everything easier, I'm just going to flip it so it lines up that way. And this is okay stereochemically because everything coming off of the ring is in plane. So now we can do our numbering. And then we can do the same to the corresponding carbons in the starting material. And then we can draw our substituents. So there's this isopropyl group coming off of carbon 2, and then each of the carbons in the dienophile have a carbonyl on them. But hold up, this isn't right yet. If we were to run this reaction as it is, we would get this, which looks a lot more like the template because it only has one double bond. So how do we end up with two double bonds in the product? And the answer may be a little straightforward, but pretty much during the mechanism, you move electrons from the dienophile to form one of the bonds that form the ring. So all we need to do to make sure that that second double bond is there is add another pair of electrons. And that can be done by using an alkyne instead of an alkene in the dienophile. So you have a triple bond. One thing to note is that when you do this, that geometry is linear because it's sp hybridized. So this would be the solution for this problem. Once again, I can start with the template. That means I can redraw the base cyclohexene. The next step is to number the carbons on that cyclohexene as well as the corresponding carbons on the starting material. Now that I have those numbered, I can go about adding substituents to the product. So I look at my starting material and I see that carbon 1 is a methyl group. Carbon 4 has a methyl group and an ethyl group. And then carbon 5 has an alcohol. Now that we have the backbone for the skeletal structure done, we can focus on the stereochemistry. And we can go back to the old rules. So looking at carbon 1, the methyl group is away, it's on the outside. So it will be away here. The same goes for the ethyl group on carbon 4. That's also away. So it'll be away here. And the methyl group on carbon 4 is on the inside, so it's close. So it's going to come to us. Now, if I were to draw the stereochemistry in, the bonds that are going away are on dashes, and the bond that is coming towards us should be on a wedge, like this. Now we can focus on the dienophile. And if you recall, the major product will normally be in the exo or the endo configuration. So this will be on A dash. And that means, if we clean this up, that this is our final solution. Good job. That's all I have for you today. Subscribe for more organic chemistry practice problems.